Hello, welcome to lecture 15 of our Essentials of Semiconductor Device Physics course. In this lecture, we're gonna derive an expression for the diffusion current. So in lecture 13, we looked at drift currents. So remember that a drift current is the current associated with a preferential velocity. And this velocity is usually caused by a force. So we first considered a simpler situation where we had a gas of particles and they all traveled in the horizontal direction, and then we found this logical relationship between the current density, the concentration of particles, and the velocity of the particles. And then we considered a more general case where the particles were allowed to move backwards and also with different speeds, and we found this more general expression where the current density depends on the average velocity. So when the average velocity of the particles is zero, then we do not have a preferential velocity. In other words, we don't have a drift current. So when this term is zero, the drift current is zero. And in this lecture, we're going to consider a situation where we're going to assume that the average velocity is zero, but there will be a variation in the concentration of particles, and this variation will cause a second kind of current, which is the diffusion current. So to make sense of the diffusion current, we're going to consider a box, and we're going to suppose that there's a gas of particles on the left side of this box, a gas of particles in the right side of the box. They have different concentrations on both sides, and in both cases the average velocity is zero. And we're going to also assume, for the sake of simplicity, that the speed, in other words the magnitude of the velocity, is the same for all particles. That's not actually true, but the way we take into account the effect of the distribution of the magnitude does not affect the reasoning we're going to follow in this lecture. So to simplify matters, we're going to assume that they all have the same magnitude. And we're also going to place z axis here to derive the expressions that we want. So we're going to use this z0 term here in the middle of the box, and our job is to find the diffusion current, in other words, the current that will arise from the random movement of these particles at the middle of the box, so in this point z0 here. So you can also consider that the box extends in the direction of the screen, so we're showing a cross-section here of the box. Okay, so in lecture 13, when we considered that all particles traveled with the same velocity and in the horizontal direction, we found that the current density was given by the concentration of particles times the velocity or the speed. Now, we cannot in principle use this equation in our new situation because we do not have all particles traveling with the same velocity. We now have a random distribution of velocities. But we can use this expression if we conceptually divide the particles into groups where in each group all particles have the same velocity, and we can characterize the velocity using the angle it makes with the horizontal, in other words, with the z-axis. So if we do that, then all particles will have the same velocity, and we can use this expression. And this is exactly what is done here. So this term is the current of particles from the left box to the right box. So it's the contribution of the left box to the current at z0. We are using this expression, but for the concentration of particles, we are using the concentration of particles in the left box but using only the group of particles traveling with an angle theta with respect to the horizontal, with respect to the z-axis. So this term here refers only to the particles traveling with the angle theta. So it's the concentration of particles whose velocities have an angle theta with the horizontal. And Vz here is the horizontal component of the velocity. So it's the magnitude of the velocity times the cosine of theta. So this expression is the same as this, but recall that here we have the horizontal velocity, so that's why we need the horizontal component of the velocity. That's why we have this term. And this equation was applied to particles traveling with the same velocity. So that's why we need to take this concentration here as being the concentration of particles traveling with the velocity theta. So this term is the contribution of these particles traveling with angle theta. And to find the total contribution, later on we need to integrate over all possible angles that contribute to the current at this point. And we can do the same, follow the same idea for the contribution of the second box, of the box to the right. So now it's the same idea, we just need to use the concentration of particles in the right box. And here this angle theta, we can consider it to be the same angle instead of the angle pointing the other direction, because now we're going to subtract this term from this, so we take into account the negative sign explicitly. So if we want to find the net current, then we have to take the contribution from particles going from left to right, so that's this contribution, and then take away the contribution of particles going from right to left, so that's this contribution. So the net current is the total number of particles going from left to right minus the number of particles going from right to left. So when we use these two expressions, we end up with this expression for the net current. So now we need to take into account an effect that we have ignored until this moment, and that is collision. So particles will collide with each other and also with the underlying atomic structure. And when there is collision, the velocity direction changes. But this expression assumes that the velocity direction is fixed. It does not change. So to use this expression, we need to consider the dimension of the box to be sufficiently small so that the particles traveling within the box until the edge where we are considering the current will not collide. And it's intuitive to understand why we need to set the length of the box according to this criterion, because particles too far away from the edge where we are considering the current will never reach this edge because of collision. The velocity will change direction. So we need to now invoke a parameter that describes the typical distance that particles travel without collision, and this parameter is the mean free path. So the length of the box is set by the mean free path because only within the distance without collision the particles will actually reach the edge and hence contribute to the current. So we use the letter L to denote the mean free path, and now we can set the dimension of the box according to the mean free path. And since what matters is the distance propagated in the horizontal direction, this length is the projection of the mean free path on the z-axis. So we are denoting it with the letter Lz. So Lz is L times cosine of theta. For example, if the particle is propagating with an angle of 45 degrees, and then the maximum distance it will propagate without collision would be L, and it will be the diagonal. And if you're assuming 45 degrees, then the projection, the distance it will propagate in the horizontal would be L times the cosine of 45 degrees. So that's why we need the projection of the mean free path onto the horizontal axis to set the maximum distance or the length of the box within which there is no collision. Now recall that since we are considering that the concentration in both boxes are different and we set a horizontal axis here, that means that the concentration is also a function of the of space, of z. Now typically the concentration will vary slowly with space, with z. And when we use the word slowly, it's with respect to the mean free path. In other words, typically we can treat the mean free path as an infinitesimal step for the concentration. So in this case, we can describe the concentration on the left box in terms of a variable z. So the concentration in the left box will be the concentration evaluated at the point z0 minus Lz. And the concentration in the right box would be the concentration evaluated at the point z0 plus Lz. We can also subtract the concentration in the left from the concentration in the right and divide by 2Lz. If we do that, we are essentially taking the partial derivative of the concentration with respect to z, because that's going to be the concentration evaluated at the point z0 plus Lz minus the concentration evaluated at the point z0 minus Lz. So there is a distance of 2Lz. When divided by this distance, we are taking the derivative as long as this distance can be considered as an infinitesimal step. So with this consideration, we can express this subtraction in terms of the partial derivative of the concentration. But notice that this is only valid if our assumption that this function varies slowly with z is true, and this is a physical assumption. And it is usually the case that this physical assumption is valid, and for our purpose we can safely assume that it will be valid. So assume that it's true, that this condition is true, we can express this subtraction in terms of the partial derivative times Lz times 2. And notice the negative sign. So the negative sign appeared because in the derivative we have this subtraction, but what we want is the other way around. So it's the other way around. That's why we have this negative sign. Now we clean the screen a bit and express the projection of the mean free path in terms of the mean free path itself. So Lz is L times the cosine of theta. And now we get that the contribution of the group of particles traveling with velocities making an angle theta is given by this expression. Okay, now we invoke the result we derived in lecture 14. So recall that rho of theta is the concentration of particles whose velocities make an angle theta with the horizontal. Now this term here is the total concentration, and this term, where omega is a solid angle, is the fraction of the total concentration of particles whose velocities are traveling with an angle theta within a small variation of the solid angle. So we derived this fraction in lecture 14, and recall that 4 pi is associated with the fact that the area of a sphere is 4 pi times r squared. So using the expression for the small variation of the solid angle that we also derived in lecture 14, we get that the concentration of this group of particles is given by the total concentration now times the sine of theta times delta phi times delta theta divided by 4 pi. So since this derivative here is with respect to the concentration of particles whose velocities make an angle theta, it's the derivative of this term here. So when we use this expression and take the derivative with respect to z, since only this term depends on z, then this derivative is reduced to the derivative of this term times this term. So it is replaced with this derivative times this term, which is showing here. Now to get the total current, we have to integrate over all angles that contribute to the current at the point we are evaluating. So recall that theta is the angle that the velocity makes with the horizontal. So if theta is 0, then the velocity is aligned with the horizontal. If theta is pi over 2, that means that the velocity is making 90 degrees with the horizontal. And if theta is higher than pi over 2, then the velocity is pointing in the opposite direction. So particles having velocities with angle theta larger than pi over 2 are propagating the wrong direction. So they do not contribute to the current at z0. So the angle theta, we can integrate it only between 0 and pi over 2, because above pi over 2 the particles are propagating in the opposite direction, so they do not contribute. And the angle phi that we defined in the previous lecture, we integrate between 0 over 2 pi, between 0 and 2 pi, because all angles phi contribute to the current as long as theta is between 0 and pi over 2. And the function does not depend on phi, so the integral over phi is just 2 times pi. So we're going to get 4 times pi here when we multiply 2 pi times 2. So it's going to cancel with this 4 pi, and we end up with this expression. So it's an integral only over theta. It's not difficult. You can solve it by yourself or look at the table, and you're going to find that the result is 1 over 3. So we end up with this expression for the total current. Okay, so we now have an expression for the diffusion current, and it is proportional to the derivative of the concentration. And of course, if the concentration is uniform, then this derivative is 0, and there is no diffusion current. This term that multiplies the derivative is denoted the diffusion coefficient. In our model, it's given by the mean free path times the magnitude of the velocity divided by 3. So as I mentioned briefly, the magnitude of the velocity is actually not fixed, so this is actually an average over a distribution of magnitudes that depend on the temperature. So this term depends on the temperature, so the diffusion coefficient also depends on the temperature, but we don't need to worry about that in this course. So we finally get an expression for a diffusion current in terms of the diffusion coefficient. It is also important to spell out the physical meaning of this negative sign. So this physical meaning is that the direction of the diffusion current always points from the region with higher concentration, like in this example, to the region with lower concentration. So, for example, let's suppose we have this situation. The concentration is decreasing as we move towards positive z. So we could represent this with a line like this, in a plot of rho against z. So if that is the case, then the derivative of the concentration is a negative number, which means that the current is a positive number. So the current will go from left to right. It will go from the region with high concentration to the region with lower concentration. And if we invert the concentration dependence, if we make it increase with the z direction, we are going to reach the same conclusion. The diffusion always points from the region with higher concentration to the region with lower concentration. So that's why when we let two systems with different concentrations to interact, after some time, in other words, in equilibrium, the concentrations will be constant because there will be diffusion of particles from the system with higher concentration to the system with lower concentration. And we learned in the previous lectures that these dynamics they are described by the chemical potential. So a difference in chemical potential is manifested as a variation in the concentration, and that's what causes a diffusion current. So the diffusion current is the current caused by a gradient in the chemical potential, as we mentioned earlier. You may have also noticed that what we actually found is the z component of the current density. In general, the current density is a vector, and if we want to find the x and y components, we can follow the same reasoning, and we're going to find that they are proportional to the derivatives with respect to x or y, depending on what component we are looking at. And depending on the material, the diffusion coefficient could be different for each component as well. But for our purpose, a one-dimensional current suffices. So we're not going to talk about vectors. We're going to still talk about a current as a scalar because our situation is essentially one-dimensional. Okay, so let's sum up what we have learned. There are two kinds of currents. There's the drift current and there's the diffusion current. The drift current is the current associated with a preferential velocity. In other words, the average velocity is not zero. And this preferential velocity is caused by a force. In our case, in our course, the relevant force is electrostatic in nature. So it's a force described by an electric field. And since an electric field is associated with an electrostatic potential difference, we can say that the drift current is the current caused by an electrostatic potential difference. Now we also have the diffusion current. The diffusion current is not associated with any force. It is associated with a gradient in the concentration of particles. And we have seen that the concentration of particles is connected with the chemical potential. So a gradient in the chemical potential will manifest as a gradient in the concentration of particles. So we can say that the diffusion current is the current caused by a chemical potential difference. So in semiconductor devices, we need both currents, both mechanisms, and all the physics of semiconductor devices depends on the interplay between these two currents and these two potentials, as we will see in future lectures. Okay, so with that we conclude this lecture, and in the next lecture we're gonna derive the continuity equation, which is again a logical relationship between concentration and current. So I see you there.